Hello and welcome to a new video where I will explain the Clark's method for instantaneous unit hydrograph development, how you can develop or generate a unit hydrograph with the help of Clark's method. This tutorial comes under the flood routing methods, and this is an example where the Muskingum routing equation is modified to generate unit hydrographs. Before beginning this tutorial, let it be clear that we have to make two very important assumptions. One assumption is the reservoir is linear, that is storage is directly proportional to outflow. That means S is KQ, where K is the storage constant. The unit of K is in time. That means hourly or minute or daily, like this. S is your storage, Q is your outflow. The meaning of that is there is no impact of inflow on the storage of the reservoir. As a result, what happens? The weighing factor X, if you remember the Muskingum equation, there are two important factors. One is X, another one is K. K is the storage constant, I have explained. X is the weighing factor. Weighing factor of Muskingum equation in this case is 0, assumed to be 0. This weighing factor actually depicts the weightage of importance of inflow and outflow in the Muskingum equation. Okay, so this is one assumption, that the reservoir is linear. Second assumption is the channel is linear also. That means there is no attenuation, only translation of hydrograph. After entering the channel, the inflow hydrograph can only translate, cannot attenuate. That means its characteristic will not change after entering the channel. Both are ideal cases, both are fictitious cases. But to apply Clark's method, you must assume the reservoir linearity and channel linearity. That means the linear reservoir and linear channel assumption you must make. Otherwise, you cannot move ahead with this problem. So, another thing is that there are some prerequisites. You must know what is time of concentration. That is very important. You must know what is time of concentration, and you must also know what is isochrones and what is the Muskingum equation. Okay. Time of concentration you can find out if you search in the internet. It is basically the time taken by a unit amount of rainfall or unit amount of water or water droplet from the furthest point of the watershed to the outlet of the watershed. So this is what is the time of concentration is. The time taken by a unit volume of water for traveling from the furthest location of the watershed to the outlet of the river channel. Okay, this is time of concentration. You can empirically determine this time of concentration or experimentally determine this time of concentration. If you want to apply empirical equation, you can apply equation like Kirpich equation, then kinematic wave equation, and all other different equations are there. Sorry. What is isochrones line? Isochrones line means the line joining the point where time of concentration is same. Among the watershed, the lines which have the same time of concentration is known as isochrones. Muskingum routing equation, there is a video on it. You have to go and refer to that video. But it is more or less an equation which is routing equation for water entering the wedge or channels. It is not generally used for hydrologic routing. Mainly it is used for hydraulic routing, but channel routing and wedge routing, Muskingum method is widely used. Okay. So with this Muskingum routing equation, you can find the discharge after the final time interval, Q2. Okay. So that is what the prerequisites are. That is what the assumptions are. So next is, if you want to solve a problem, what will be given to you? So I have written here given. Given will be the K, storage constant. Okay. Del travel time of hydrograph will be provided also. Del TC will be provided and inter-isochrone area will be given. What are they? Take this example here. Time, this is a problem where time is provided, interchronal area is provided. Then you have to find out the Q2 to draw the unit hydrograph. So with the help of Clark's method, you know this is the time, this is actually the time of concentration. So here from 0, suppose the time taken by a water droplet from the furthest point to the outlet is 12 hours. Okay, now this 12 hour is equally divided into n parts. Okay, suppose they are equally divided into 6 parts, right? So if n is equal to 6, then del time of concentration will be 2 hours. Okay, so the del time of concentration will be 2 hours. Sorry. Now for every time of concentration, you have to calculate the value of Q2, because that is the way you will generate the unit hydrograph. Because you see, if this is the unit hydrograph, then what happens is, this is your del TC and this is your Q. Okay, so to find out Q at every del TC, you need to know what is the del TC. So you have to divide the full time of concentration or the maximum time of concentration that a water droplet is taking to reach the outlet from the furthest point of the watershed. That need to be divided either by the way the problem shows it. Here the problem has shown it that you divide the maximum time taken by your water droplet to reach the outlet from the furthest point of watershed into 6 segments. So if this is the watershed, okay, and this is the furthest point of the watershed, from here to here, this is the outlet, correct? So from here to here, the time taken is 12 hours. This is your time of concentration. Now if the problem says that you divide it into 6 parts, 6 equal parts, right? Then each of the time of del TC, or you can say or you can say the incremental time of concentration del Tc will be 2 hours. Sorry. If they say that divided into 4 parts, then you will divide it into 3 and del Tc will become 4 hours. Then this will also become 4 hours. But the accuracy will not be very high. Right? So 2 hours, you can divide it into 12 parts also. Each part of 1 hour duration. That is also can be done. Right? But to do that, the question or the numerical will also need to provide you with the intercoronal area. You see here from 0 to 2, so whatever intercoronal area, as I have said, the line joining the points which have the same time of concentration. So it is assumed that you can divide this watershed into 6 isochronal area. Now all these lines have the same Tc, that is correct. Okay, all these lines have the same Tc, that is correct. But the area within 2 line of Tc is not same with the other area in between the 2 different Tc. That means if this is del Tc1 and if this line is del Tc2, this is the inter isochronal line area, and this area is here represented as AR. Okay, inter isochron or isochronal area, and this has to be given, otherwise this problem you cannot solve this problem. So for this 0 to 2, isochronal area is 3 square kilometer, and so on. After 2 to 4, there will be another isochronal area. For 4 to 6, another isochronal area, and so on. Sorry. Right? So, what will be your next job to do to solve the problem? So, I think you understand your K, you understand your travel time, that is the terms of concentration, you understand what is del Tc, and then you understand AR. Now K will be given in this problem, K is given as 12 hours. Okay? Okay? So, what will be your first step? You know, as C0 and C1 will be same as there is no X, right? X is equal to 0, so C0 equals to C1 equals to this value. Look, this has come from the Muskingum equation. Okay? So, first 2 terms of the Muskingum equation is equal in this case. Because there is no X, so there is no impact of X. So, first 2 terms of Muskingum equation is same. So, that is why what they have done is they have used the same formula to calculate C0 as well as C1. Sorry, and that is equals to 0.5 into del Tc. Del Tc in this case is 2 hours. That is also known to us. This del Tc is 2 hours. Del Tc is also 2 hours. Multiplied with 0.5, multiplied with 0.5, and this K is 12 hours. That is also known to us. Correct? Sorry. So that is also known to us that K is 12 hours provided by the problem. Del Tc is 2 hours calculated from the time of concentration maximum type of concentration data as provided by the or as given by the problem itself. So here the TC is, maximum TC is 12 hour. So del TC is 2 hour because 6 parts you have to make. So del TC is 2 hour, del TC 12, K is 12 hour, K is given as 12 hours. So you can find out C0, and C0 and C1 is same. So after calculating any one of them, just multiply with 2. Right? So that is why here in the equation of Q2, this is 2C1 I1. Any one you calculate, either C0 or C1, and then multiply it by 2. And then you have to multiply I1. Multiply it with I1. What is I1? I1 formula is given here. I1 is equal to 2.78 multiplied with half of the intercronal area of that time scale. That means from 0 to 2, intercronal area is 3, divided it by 2, that is 1.5. They'll multiply it with 2.78. That will give you the I. Okay, so here actually what they have done is I1 is equal to 2.78 multiplied by AR by 2. 2.78 divided by 2 is 1.39, so they have directly given 1.39 into AR. But the actual case is that. So I1 you have calculated, already you have calculated C1. There, so easily you can calculate 2 into C1 into I1. For the first time scale it is 0 because before that we do not know. This is the initial value. Na? Initial value. So initial value is 0, so everything will be 0. First value is 2 hour, after 2 hour. Intercronal area for that is given as 3 square kilometer. I1 you have calculated from here. Then what happened? How you have calculated? 1.39 into multiplied by AR. AR is your 3 square kilometer. It is coming 4.17. And then you what you do? C1 you know, right? C1 you know. 2 into C1 Y you know because C0 equals to C1. Sorry. Multiplied by I1, this one. So it is coming up to 0.64. Next is C2Q1. What is C2? Calculate with this. K minus 0.5 del TC, K plus 0.5 del TC, that is C2. Remember this del TC will be always 2 hour for this problem. Okay? And K will be 12 hour. So C2 is calculated. Now you say what is Q1? Right? Sorry. So as this is the entry point, Q1 will be surely 0. No discharge is there because this is the entry point. It is just going to, discharge is just going to start. So Q1 is 0, so this entire point goes 0. And now for the first time scale I am saying. Now what I will is how to calculate Q2. Q2 is this one. Q2 equals to 2 C1 I1 calculated, found to be 0.64. C2 Q1 is 0 because Q1 is 0 because at the first scale there is no discharge. Now the discharge will take place. So this C2 Q1 is becomes 0 because Q1 is 0. So only 0.64 remains. So Q2 become 0.64. Right? So you can understood that how we have calculated Q2. Now remember that we have an assumption that this is a linear channel, and also you know that for every del T there is isochronal area, right? Because inter-isochronal area is there, and when some flow is coming into it, right, and going out to it, that means let me draw a clearer picture. Suppose I think let us do it like this. So suppose what happened is, this is the watershed, and the water droplet is coming like this. Isochronal area is like this. This is the same point TC, right? This I have already discussed. What is the thing is that there will be 6. So 1, 2, 3, 5 and 6. Now you see, well, water is entering here now. So for this area, this is outflow going out, but for this area, this is inflow. Correct? So whatever is going out from one isochronal area to the adjacent isochronal area, then whatever flow is going out of that isochronal area becomes the inflow to the next isochronal area. That is what I am saying. So well, Q1, let it be Q2 of the first isochronal area is going into the second isochronal area, then this Q2 will become I1 for the second isochronal area. Just check, but this is, all this isochronal area is cascaded. If I represent them by a square like this, all the isochronal area is cascaded. So what is cascading? Outflow, output from the previous is the inflow to the next. Alright. Right? So if this is wall, this is 2, 3, this is 4, this is 5, this is 6, there is no 7. So the outflow from outflow from wall, Q wall, right, is the inflow for 2. Again, outflow from 2 is the inflow of 3. Again, outflow of 3 is the inflow of 4, and so on. So you have to use this concept at what time? In the next time scale, that means the 4th hour, 0 to 4, there will be an isochronal area. There you can calculate I1 also, because here remember this subscript I1 or Q2 represent the time, the time interval. I1 means the first time when the inflow take place, right? And Q2 represents that the final time interval when the Q or outflow goes out. So don't confuse with this subscript with the other subscript. So this Q2 is always outflow from the isochronal area, and this I1 you can take will be always inflow to the isochronal area. This subscript 1 and 2 does not have any significance related to the isochronal areas. Always there will be inflow, there will be outflow. So I1 Q2, now this 0.6 flow is the outflow from the first isochronal area. So in the next isochronal area, this Q2 0.64 will become the inflow, or rather I will say the Q1 of the next isochronal area. So you can say that Q2 you can always assume to be equal to Q1. Not assume, it is true, because whatever coming inside to the isochronal area, that is going out to the next isochronal area. So basically all these isochronal areas are in cascading order. So Q2 will be equals to Q1. Then you multiply that C2 with Q1, right? So always remember that Q2 of the previous isochronal area is the Q1 of the next isochronal area. Right? So basically with this, for each of the type scale 0, 2, 4, 6, 8 till 12, there will be a Q2 that you can calculate, and with the help of that you can easily draw a unit hydrograph. So that generated unit hydrograph is, of course it is synthetic, it is not real, it is artificial, but this is one of the most accurate way to generate a synthetic unit hydrograph. So this is proposed by the Clark. So this is what is the Clark's instant unit hydrograph generation method. So just to recapitulate, first calculate C0 or C1 and then multiply the value with 2 because C0 and C1 is same here because X is 0. Because of the assumption that reservoir is linear, low impact of inflow. Sorry. Then try to calculate C2 with the equation B. So once you have calculated C2, calculate I1 with the help of isochronal area and these formulas, equation C. They'll make a table. You will be provided with the storage constant, which in this case is 12 hours. Sorry. Travel time of the hydrograph will also be provided. So 0, 2, 4, these are all will sum up to the maximum time of concentration. In this case, 12 is the maximum time of concentration. We have divided into 6 parts. So each part becomes 2 hours. So del Tc is becoming 2 hours. Now for every del Tc, you have to calculate Q2. Use the equations I1, 2 C1 I1, C2 Q1, and then find Q2. So just remember that Q2 of previous isochronal area is the Q1 of the next isochronal area. That is one assumption. And at the first time scale, each of the value will be 0 because that is the initial condition. Outflow has not taken place yet. So that is why in this case, you see, in this case, Q1 is where it is, Q1 is taken as 0, that is why C2 is 0. Right? Another way to describe is that you see Qt in the first time scale 0. Qt is 0 here, so Q1 is 0. So Q1 is 0 means C2 is into 0 is 0. Next, Qt is 0.64, that is why Q1 is 0.64. Multiply with C2, then they'll carry on like this way. Okay, so with this, I finish this tutorial. So always remember, for Clark's method of instantaneous unit hydrograph, you have to move from equation A here, then to equation B, then to equation C, and ultimately to find the ordinate of that instantaneous unit hydrograph, you have to use equation D. So for any query, kindly comment me, and I will answer as much as I can. Thank you, and see you next time again.